So I'll talk about the proposed relationships between consciousness and the particular type of online compositional learning system architecture. And the details of this is in that preprint that's shown there. I'll start with motivating it. So what's the end goal for a theory of consciousness like? It's something that has formal objects and it defines functional relationships with some formal objects, some components that describe experimental observations. A typical experimental observation is masking, contrast, sequence integrations, and all these other things that cognitive science kind of produced. Neuroscience measurements, but also consistent, of course, with our prior knowledge and general science knowledge like physics and neurobiology, and have some arguments about evolutionary origin, plausibility, and stuff. But also specific to consciousness, it has to address the first-person observations. The way I deal with the first-person stuff is basically saying these are amateur observations that we all make, right, as observing systems. So a theory should say how come a system's capable of making observations, first of all, and why the observations are as they are. Why do we all seem to experience sort of a unified yet differentiated conscious contents? Why are we able to associatively recall these experiences? We have working memory and things become globally available, and we seem to have intuitions about phenomenality, and we all experience valence associated with these perceptions. So those are all the important things that actually needed to be described by something like a full theory of consciousness. And then the definition of consciousness would then sort of fall out of the theory, sort of like before the theory of electricity and magnetism, there was no formal definition of electromagnetic field. So a definition of electromagnetic field is a formal component of the theory itself, right? So the consciousness gets defined a similar way. So motivationally, I'll start by saying that humans and animal learning is very different from what present machine learning systems do. We are in particular capable of very efficient online and extremely scalable learning, so we can learn very large perceptual and action spaces. And the structure of our models seem to be not only deep but compositional. And compositional learning is, again, something that is a problem with present robotics. So robotics cannot make learning models that consist of units that once learned can be used out of the context and be applied in different contexts to learn other things. And we do that great. It seems to be done through declarative memory. So declarative memories are first closely associated, declarative memory formations closely associated with consciousness. Consciousness contents is the contents of declarative memory. They have the compositional structure. We're capable of learning them from essentially single exposure, single examples to an episode. And they underline a lot of our perception and action learning. So how would a compositional learning system work, right? So what are the properties of compositional learning as opposed to just any kind of learning? First of all, it needs to find new causes, new units, right? So it's a compositional system. It consists of, the hypothesis consists of units. These units have to reduce the error, right? So it has to predict something. But they also have certain regularization biases, simplifying them. So they're going to have few features. We want to find causes that are persistent in time and can serve as features for then learning other causes later. Comparing to the bottleneck that we often associate with consciousness, what is in consciousness is a small percentage, small subset of all the perceptions that the system that we are making at any given moment, right? So why is that? Why are we selecting a small subset? Well, again, because we are finding something that's unique to the present moment, that's not explained, and that has that persists over some reasonable period of time, typically 0.2 to 1 second, and that consists of a small subset, has a small subset of concurrent features, right? So basically, the consciousness bottleneck is very much reminiscent to what a compositional learning system would try to look for to learn. Right? So the hypothesis here is that consciousness is what it's like to be a compositional learning system that specifically combines a hierarchical generative model such as predictive processing framework, but also that learns new causes within this model by binding, by feature binding. And I'll tell you exactly what I mean by these two terms. The feature binding addresses the issue of fast Bayesian learning, fast Bayesian learning to add new causal structures, to discover new causal structures and add them to the hypothesis. So a short introduction to sort of bidirectional dynamic models such as categorical predictive processing. Basically, your degrees of freedom are these cause units that could be they're not individual neurons. So they're something like neurobiologically, maybe neural columns or some subnets of neurons that encode a state space variable. So these are states of causes that could be understood as, for example, likelihoods of individual causes in a categorical predictive processing. And they are connected to each other by learned weights, which encode the inference prediction relationship. So causes in a higher layer predict causes in the lower layer, while the causes in the lower layer then communicate their prediction errors up so that these inferences can be adjusted. And so there are two sets of dynamic relationships here. So one is a faster minimization that proceeds along local rules that basically approximates Bayesian inference of the states based on the inputs, based on the sensing data. And this is proceeding dynamically, and these causes can encode things like delays due to distinct sensory latencies, as well as sequences, right? So like a melody, a cause for a melody would consist of a sequence of tones and be inferred from a sequence and then predict a continuation of that sequence. But also there's a learning dynamic, and this is all conventional predictive processing, right? So I'm not just kind of rehashing this. The learning proceeds by adjusting weights over time to minimize prediction errors within this set typology. Also, actions can be generally also encoded within the same system by basically saying there are certain causes that are actuators, and whatever is predicted for them happens. And so this network can encode both actions and perception. And then it's been argued to be somewhat neurobiologically feasible. I don't have any expertise to say one way or the other. Predictive processing, as currently conceived, has significant limitations. One is as Stephen Fleming told us today, has no commitment to separating conscious versus unconscious contents. It doesn't tell us how to do it. There's also an important thing that there's a fixed state space assumption. So there is lack of new causal structure learning, right? It doesn't add or subtract causes normally, right? So, and weight updates have to be gradual because weights that have already been learned on many examples, and there's no reason for one example to sort of lead to very large weight updates, right? So again, we don't have this ability to do, or don't have a reason to do discontinuous learning within that model, and it's not explicitly compositional. So what I'm proposing is that we can combine predictive processing with a different learning mechanism, which is learning by feature binding. What I mean is, suppose there are a few features within this predictive processing framework that occur at a given moment with large prediction errors, so nothing else predicts them, right? So there's an unpredicted shape of a car that's represented over here. There's an unpredicted color red that's represented in a different location in the brain, and there's an unpredicted location on the left. And these things occurred within the predictive processing network in the brain at the same time, and they persist over a significant period of time, right? So we can introduce a learning mechanism that basically has a learning bias that there must be a hidden cause that causes these things to appear together. We just haven't learned it yet, right? So one thing we can do is we say, well, there's a hidden cause, let's add it to the structure, right? So we'll say there's a new cause that we're going to create instantaneously. We're going to call it the car, right? That predicts precisely the features as they occurred, right? So all these prediction errors of these features that were not predicted before sort of go to zero, with the likelihood of the car always sort of instantaneously going to 1, right? So we have this new cause that we just added to the predictive processing model, right? It represents, it provides immediate full prediction weights, right? So it's a discontinuous learning thing. It also has a generative power, because now if one of these things, for example, stop being inferred from sensory data, right, we're distracted or obscured or something, this cause here will predict that feature, right? So now the model dynamics has changed because the occurrence of this actually predicts that. Okay, so what do we do with this? Well, it could have been a fluke, right? So by Occam's razor, we're going to attenuate these weights over time if this cause is not reinferred continuously or repeatedly, right? So if this cause is actually not useful to predict sensory data, we're going to attenuate the weights and forget about it. On the other hand, if this cause happens to be useful and it's continuously repeated, reinferred, and it continues to minimize prediction weights for these features, we're going to keep that and refine it based on additional data, right? So we're going to refine these weights based on how these causes correlate, right? Okay, so this is the learning mechanism. And now what I'm going to talk about for the rest of the talk is, what does this imply? So we have a system like that. What does this imply? What behavior would we see? Well, first of all, let me add two things, right? This binding is parallel, right? So we can have a new cause for the car on the left, red car, loud car on the left, and a green tall tree on the right, right? So similar mechanisms, we've just created these things. They're temporary causes. That's why they're dashed. They might be forgotten after a while. But the binding bias is hierarchical, right? So these two causes do not have anything that predicts them, therefore they have large prediction errors. They have large prediction errors, we want to bind them into a new cause again. And so ultimately we basically bind everything that's not predicted, like the context and everything else, and the new causes into this one cause that's the description of the present moment, right? So there's this one cause that we formed in our predictive processing model that represents the present moment. Specifically, essentially the present moment is represented by a shallow tree of new and existing causes that are unpredicted at the moment. And it's specific to the present moment, right? Only unpredicted stuff is bound like that. And the known causes that were there serve as the code alphabet for creating these hierarchical descriptions, right? So what I would argue is this is precisely, out of all the features that are being inferred with non-zero likelihood at the moment, this structure is precisely the contents of consciousness. The reason being is, first of all, this is subject to associative recall. So when you have these causal structures and then some subset of features reoccur, such as, in this case, sort of location on the left and the motor sound coming from that location, right? So we kind of represent the sound and the left. And the context is similar, so we kind of infer this previous episode. All these things together kind of predict and help us to infer that there is that car that we've created that cause for, and therefore it has the car shape and the color red and stuff like that, right? So by re-exposing the system to a partial subset of sensory data that's similar to the one we had before, we can have these situations where there's associative recall of the learned causes. And that can be rebound if there's unpredicted stuff again here, then this can be rebound, so we can form repeated recalls of, so we can call a memory, essentially create a memory record of stuff that occurs to us. So there's a short-term memory record that this mechanism allows one to create, right? That's associatively recallable and automatic, which is basically the underlying ability necessary to make and recall observations. So that's how this system can make specific observations about its specific things that it encountered that it did not predict at various moments. The second thing is, how can we maintain that VCAR in working memory without constantly looking at it, right? We cannot have an action that acts directly and predicts the car directly, because the cause for the car has just been learned, and therefore it's new, and we couldn't have learned an action that predicts that. But we could have learned an action that predicts a particular spatial location, right? So by paying attention to a particular spatial location, right, that spatial location comes up with high likelihood, but it's related to the car, right? And so that type of mechanism would, in principle, allow one to maintain the car and all of the all of its features at non-zero likelihood at the present moment, even without the direct sensory inference. This bound object becomes globally available. What does that mean? Before, the car shape was not connected to the color red or the sound or the location. Now it is. And so if this system is, for example, prompted by a feature prompt of, like, what color is the car, right? So there's the word the car invokes the car, which infers this object that predicts the features that the car had, such as the color. And then the prompt for the color then makes the system, take an action that depends on whether it's a red or green here. And the red's active with non-zero likelihood, and the green is not. And so there's a report of red that the system generates, right? So this is how binding the shape and the color through this new cause made this object kind of appear to be globally available, because any action, anything that acts on one of these things can have a consequence that's related to any other one of these things, right? Which before it could not, before this binding has occurred. Okay, so how can this describe, some of the typical experimental paradigms? So in order for this binding to occur, the stimulus has to persist for a long enough time and with large enough prediction error, right? So if it does, it gets bound and it's recallable and reportable. If the masking occurs before that stimulus persists for long enough, after the masking, the estimated likelihood of the stimulus being present goes down, right? So that's what the role of masking, right? And this delta t is smaller than the tau needed for the binding. Essentially, the stimulus was present there, but it was present too short a period of time. It never got bound with other things into the present moment. It's not reportable. It's not seen, right? The same thing with contrast. If the stimulus is presented with high contrast, it's bound and reportable. If the stimulus is presented with low contrast, the prediction error associated with that stimulus is low, and therefore it never exceeds the threshold needed to be bound and therefore be reportable and recallable. Okay. Learning sequences, if two things are separate, they're bound separately. But if two new things occur with a short enough delay, the system binds them together into a sequence cause, right? So now there's a single cause that represents this delta t and that. And then once you have that cause learned, then when this reoccurs, that cause is inferred. It drops the prediction errors for these things, and then that cause is what's being bound. So now you have mandatory integration. You do not have the ability to recall these things separately. Instead, you're recalling this, right? If a third stimulus reoccurs even a short period of time after mandatory integration occurred, and this has been observed experimentally, that if the third stimulus occurs after a short period of time, that stimulus is actually bound to the inferred cause, to the integrated cause, right? And then you have two of these things that are recallable and reportable like that, right? So again, we don't have the ability to tell S1, S2. Instead, we tell this, but then we see S3 even a short period after that, all right? So this is Stephen Fleming sort of said. Basically, it's a slide that follows that. So there's got to be, hierarchically, naturally, this system learns causes that are about its internal states. Right? It learns causes that discriminate whether it's what I'm seeing, this tree here, whether it's a direct sensory experience or imagination, or it's there, but I'm not looking at it, therefore I'm not experiencing it, but I know it's there. Right? So I have these sensory cause for a sensory experience. Right? And the important thing is that sensory experience arising cause is as real to me as a system. It has the same properties as the causes for physical objects. Right? So then I feel like I want to have the same type of explanation for this thing as I would have for those things. And for those things, we have physical theories. And for this thing, we have nothing. Right? So that gives rise to the intuition of the hard problem, something to be explained that we don't know how to explain. And now, by understanding that both of these things are constructs, inferences from our transparent models, we can basically understand where they provide an answer to the meta-hard problem of consciousness. How is this useful? Why is it biologically useful for an organism to have this type of stuff? So first of all, it can encode perception action policies that the organism follows. Okay, great. This is active inference. That's been lots of discussions about that. And there's no problem with that. Like, how do we learn actions and perceptions here? So we have rewards that are indicators. They're short-term, myopic, biology-given indicators of what's good and bad for us from low sensory data, right? And so these are rewards. But what we need to learn is we need to learn the value of the present states. We need to be able to predict the rewards within sort of reinforcement learning framework. And the way we do that is on the perception side of this model, we basically assign each of the causes a certain valence, and a certain scalar value that is predictive of this particular reward type, right? So, and we can learn these things. I'll tell you how we learn these things. So now we have these values, valences assigned to these causes. We take a derivative of that, and we compare it to the reward. And if there's an error, then there's not predicted, there's a reward surprise. If there's a reward surprise, what we do is we propagate that error back to the causes that were just used to infer it, and we basically modify the causes that were active over some short period back in time, right? So there must have been some causes active in time just immediately before this that are account for this reward error, right? So we're going to propagate that reward error back. So that's how we can learn various types of values of the present state. These reward detectors are across different modalities. They have different emotions or different things that make us feel good or bad. They have different biological modalities for these rewards, and there's different circuits, and all these types of rewards, all these different types of emotions are essentially perceptually encoded in the perceptual part of the system, right? So then the perception predicts, makes us feel these things, and essentially they are there to predict and correctly interpret the value. I'm almost done.
Over your time.
Yeah, the action, and then we can use these, we can sum up these valences and use them to learn whether the actions we just took were good or bad, right? So we kind of have it, we can close the loop and say, well, if there's a positive value reward surprise, then the action was good. There was a negative value surprise, the action was bad and should be forgotten. I'm going to skip all this stuff. Of course, the future work is, does this hold water as a machine learning approach, right? So can this converge? I don't know. It seems to explain a lot of empirical data right now, but like I don't pretend to know a lot of it, right? So is there some empirical data that can falsify this? I'd love to know. Then we can design other hypotheses to test this, of course. And if this is true, does that provide a sufficient explanation for what we want to explain? And what are the wider implications? So acknowledgements, thank those people for useful discussions and the summary. And this and more is described in the archive posting there. So if you're interested, please take a look.